Hello everyone. Yesterday when preparing for this opening, I suddenly realized that if I pronounce the name of this conference a little bit differently, I will have actually the greeting. So let me try that. Hi, load. Thank you. Yeah, so we've done that. It worked. My name is Valentin. I'm a PHP developer and enthusiast and contributor, and today I will be the host in this hall, the hall number 4, named Ashot Yevkrat after Armenian's famous Tsar. And so I will help you to use our conference. If you have any technical issues, any questions, you can always find me. I will be over here. And I will help our speakers to find their way to the stage. So today we have a really wide range of different topics, of different talks. So we'll talk about optimization, about profiling, about microservices, about algorithms. So the day is promising to be really busy, but very interesting. So I wish you all good luck and learn a lot today. And so we're basically ready to start. Welcome to the stage. Let's ask Igor Solovyov from Yandex. Come here. So Igor will talk about optimization and profiling in distributed systems. Thank you.
Okay. Thank you. Hello, everyone. I'm glad to see you still so early in the morning. I deliberately gave my talk a kind of provocative title, but I believe that it may be interesting for you. Because we all on high lot, because we love high performance. So we love optimized programs. And in fact, some of us hate optimizing. So it is very convenient. So it is crucially important to have convenient tools for such devastational activity like profiling. And the most important tool is a profiler, I suppose. A few words about me. I'm Igor Solovyov. I'm a developer in the Yandex advertising infrastructure team. We develop a service with about 1 million requests per second. It processes about 1 million events per second. It has about 100 terabytes of data accessible in several milliseconds. And in our team, I specialize on data structure optimizations, on big data analysis, and I create our distributed profiling tool. So first of all, let us start with some notations. I think we all know what a profiler is. Distributed profilers are different from more familiar local profilers in one way. They aggregate data from multiple hosts. Profiler obtains stack traces and the amount of time the program spent in each stack. This information is very useful but barely usable, and it is way more convenient to use some visualizers. I suppose that the best visualizer is Flame Graph. The x-axis shows the stack profile population and sorted alphabetically, and the y-axis shows the stack depths counting from 0 at the bottom. Each rectangle represents a stack frame, and the wider rectangle is, the more often frame was presented in the stacks. Original flame graphs use random colors to help differentiate adjacent flames. Now I will try to convince you that if you have a distributed system, an ordinary local profiler is certainly not enough, and you need to buy a brand new distributed profiler for your system. I will list some reasons why you should try a distributed profiler. First of all, a distributed profiler is still a profiler. So if you use or want to use a profiler, you can use a distributed profiler as well. You can use it for exploration of targets for optimization, for estimation of your optimization profits, and so on. I suppose that the most noticeable problem with convenient local profilers is their complexity. If you want to have even a basic understanding of such tools like perf, you should read several long articles. And Brandon Gregg and his website are your best friends in this case. But even if you don't want to understand it and you just want to use it, you still should keep in mind a whole set of details. For example, what parameters you should use, which flags you should compile your program with, how to visualize your stacks, and so on. If you profile only from time to time, you possibly don't remember the list of actions you should do to obtain a profile. Another annoying thing with traditional local profilers is that you cannot take just a prepared flame graph. You should spend a lot of time writing a profile, and the less invasive you want to be, the more time you need to spend. But if you have, for example, 100 hosts, it would take 100 times less time to obtain the same amount of stack traces. The difficulty of historical comparison is another obvious issue with local profilers. If you use only a local profiler, you can say nothing about history. If you want to compare two different versions, you need to make measurements, deploy a new version, and make measurements again. It may be very annoying. The next problem is that profiler can have a substantial impact on the performance of the application being profiled. Every profiler, including, of course, every distributed profiler, has some impact on the performance of the host and the measurement itself. Let us imagine the following situation. You start to profile a host. You have only one host, so sampling is pretty frequent. The host degrades in comparison with other hosts. Your balancers try to ignore the host. Congratulations, you have just measured a degraded host with an unrepresentative workload. It is similar to the observer effect in quantum mechanics, in which the act of observation disturbs an observed system. It is Schrödinger profiler, if you like. I hope that I have convinced at least some of you that distributed profiling is a thing, and now you want to build such a system. Well, I think that we should start with the design of our system. We should at least specify what the type of profiler we will use and how many samples we need to build a decent profile. Let's start by choosing the type of our profiler. There are two main classes of profilers: sampling profilers and instrumentation profilers. Sampling profiler just stops your program at a random point and prints a stack trace. Instrumentation profilers may be also called counting profilers because they change source code of your program in order to collect additional information about function calls. So they kind of count it. Here you can see the list of possible instrumentation profilers. It is a really noteworthy approach, but it has a set of problems and limitations. I have listed some of them on this slide. First of all, instrumentation has a dramatic impact on the performance of functions, especially the smallest ones. For example, inserting an integer into a vector is significantly less expensive than writing a stack trace to a storage. Another problem is that it may change not only performance, but even the behavior of the program itself. This may lead to very sophisticated bugs. These bugs are called Heisenberg bugs. It is too much quantum mechanics in my talk, I suppose. Our team prefers to use flame graphs, not just stops. Of course, you have seen flame graph. We want to see most of our functions, not just the chosen ones. And we don't want to decrease performance of our application drastically. So sampling profiling is not a good option for us, and sampling profiling is our choice. Now I want to estimate how many samples we need to build a decent profiler. I will pretend that I'm a mathematician to calculate this number. And the best way to imitate a mathematician is by using Beamer slides. Bam. Let us create a small probabilistic model of a sampling profiler. The profiler pauses the program at a random point and prints a backtrace. So we may consider this printed backtrace as a random variable x, and the sample space of the random variable x is a set of all possible stacks in our program. But it may be not very convenient to work with raw sample space, and it may be easier to work with indicators. Let us assume that we have chosen a stack S, then the indicator random variable for a stack S is defined by the following rule. It is equal to 1 if the random variable is equal to the stack we have chosen, and otherwise it is equal to 0. Let us consider the following sequence of estimators. According to the central limit theorem, this sequence of estimators has a normal asymptotic distribution. So what it means, if we take a large enough number of observations, mean of our indicators would be distributed almost normally with certain parameters. It allows us to estimate the relative error. The distribution is almost normal, so we can apply the 3 sigma rule to estimate this number. For example, if we want to consider 1% events, by time I mean, with 10% accuracy, we should take at least 10,000 samples, or 90,000 if we want 99% probability. Well, I have highlighted my profiling theory a bit. Let us now consider our system in a more practical way. On this slide, you will see a general scheme of our distributed profiling tool. In the beginning, on every host, we obtain stack traces with the help of a local profiler or some substitute for a local profiler. Then we write these stacks from every host to a common data storage. This data storage should support analytical requests. A user may then make a request to the storage and draw a flame graph if the user has a very specific demand. For example, if our default aggregational rules are too coarse, or it is necessary to collect data from a certain set of hosts. But for generic requests, we have a MapReduce operation that processes our data, and we use process data in our web server to answer generic requests. The first question we should answer when we create a sampling profiling system is how to extract stack traces from a running application. Of course, you can use a conventional local profiler, but there are at least 2 more ways to do it. It is an interesting fact that if you have a large enough number of observations, you don't even need a local profiler to build a distributed one. You, for example, may use debuggers. A profiler that uses a debugger is called a poor man's profiler. It is a well-known technique, but it's kind of useless when only one host is involved. But it becomes pretty efficient when you have a decent number of hosts. On this slide, you can see the full technology demonstration. The full technology consists of 2 parts, a GDB script and a bash command to run this script, to execute it. The GDB script does the following. In the first row, we ask GDB not to divide output into pages. Then we define a command to print a backtrace. Further, we apply this command to every thread in our application. And in the end, we quit. it is pretty much whole technology. It is not the only possible solution to use GDB. You can use a signal-based profiler. It is way harder to write such a profiler. It requires an additional flag or using of lib-unwind, but I suppose it's still worth it. GDB is a good substitute, but it has a set of problems. It takes a week to collect enough profiles with GDB, if you have only one host, I mean. And you need less than 2 minutes to collect the same amount of stack traces if you use a signal-based profiler. And also, GDB can be dangerous for your service if your service should answer requests with low latency. So it is kind of hard to write it by yourself. So on this slide, you can see links to a talk on this topic and a link to a ready-to-use library from Google. Okay. There is a problem that cannot be solved with using of conventional local profilers. It is always interesting to know how a product feature affects the performance of your application, but it's almost impossible to do with conventional local profilers. And using of GDB or a customized signal-based profiler may solve this problem. Now I will explain how you can do it. I will show you how to do it for a thread-based system. You can adapt it for a fiber-based system with replacement of thread local variables with fiber local variables. The idea is pretty simple. Both GDB and signals operate with threads. Therefore, if we put data into a thread local variables, it would be connected to a corresponding stack trace. So for every interesting for us piece of data, we create a thread local variable and put data into this variable. Then GDB can extract this variable when it attaches by calling the getter function. On this slide, you can see that you need to add only one string to support this feature in our GDB script. We add a call to our getter function in the define section. As a result, information about this stack would come before each of our stacks. We use such calls to collect information about our active A/B experiments to our stacks. I also want to highlight stack aggregation. We use a MapReduce operation to aggregate data. If you don't preprocess your data, it's quite easy to reach almost 1 billion samples per service. In some cases, it may be very time-consuming to operate with all such data on every request. But in our team, we almost always use day or week flame graphs. So we decided to use aggregation by day. It decreases the size of our base dramatically, and this is still sufficient for most of our needs. Let us consider an example of such aggregation on a synthetic stack. Of course, we have no such stack traces in our application. We apply a MapReduce operation to all of our stacks. First of all, we replace a stack trace text with a special ID. The same ID identifier will be used for identical stacks. Then we replace the timestamp of the stack with the corresponding date. I have already mentioned that we have our stacks provided with additional information about active experiments, and we aggregate our stacks based on active experiments. So we create an additional row for every active experiment, we also keep a row for the default settings. Then we choose rows with identical aggregational keys and count how many times we have encountered each one. An additional trick we use is partial sums. We often compare profiles for time intervals. For example, the last week against the week before. So a lot of queries contains some on the interval like requests. It is convenient to use partial sums to answer such requests. You just extract value at the beginning of the interval from the value at the end. Therefore, you need one array extraction instead of iterating over billions of objects and inserting them into a hash map. I hope that I have inspired at least some of you to try distributed profiler. If you are a developer, you probably want to know how your applications work. If you are a manager, you probably want to know how your applications and your developers work. Profiling and flame graphs are good tools for this problem. But conventional local profilers like perf may be very inconvenient and may have a lot of problems. A decent system of distributed profiling may solve these problems and make your life a little more pleasant. You may face some problems if you decide to implement it, but I suppose that it is totally worth it. Thank you for your attention. Leave your feedback, please.
Thank you. So, any questions? Okay, please. Now we have a helper who can give you a microphone. Or should I give mine? Oh, okay, here we go.
Wow. Okay, let's loud. You describe two kind of profilers, and when you describe sampling profiler, what about eBPF? Do you use eBPF in your distributed profiler?
We don't use it now. Now we don't use eBPF profiler. We use a customized signal-based profiler, and it kind of solves most of our problems, but it is interesting to implement it.
Okay, and which frequency to make samples?
If we use GDB profiler, it is kind of
fork of GDB and wait when they create big trace.
Yes, it is kind of dangerous in case of.
I mean,
if you mean signal-based profilers,
yes.
We sample at 100 samplings per second.
Standard. Okay. What about Rust and maybe Golang? Do you profile this application with this language?
In our production, we use only when it connected with high performance. We use only CPU, C++ at this time, as far as I know, Google Go from Go. In the standard,
Golang by default doesn't provide dwarf structures which could extract flame graphs and could extract stack traces properly.
I mean that Golang already has some libraries from Google who supports a special format, profile prota,
yes,
and we use the same format. So if at some times we will have Go production, we will be able to collect, to add this profile protos to our system.
Okay, and last question, how you scale up your storage? If you have hundreds of servers and use 100 samples per second, look like you use pre-aggregation. And how long you store your raw data?
Okay, it is. I will. As the beginning, I will answer the last question.
Switch to from Barbarian language to native.
No. This is an international conference, so it's better
We
to try to English first.
we keep our raw data for a month, I suppose. It is almost always sufficient for us, but it is kind of. I have a kind of cheat answer because we already have good infrastructure. So we have a message broker, we have a dynamic and some MapReduce clusters. So it is kind of easy in our case, but but we in some cases we still use pre-aggregation, yeah, of course.
Thank you. Any other questions? Okay. And I would like to remind our online participants that they can ask questions too, and I will see them in the chat, and I will repeat them for the speaker. Please, your question.
Hi, thank you for your talk. As I understood, this profiler stops the execution of program and collects stack traces.
When GDB-based profiler is involved, it kind of stop whole program. It may be a little more better when you may stop only a thread. In general, it takes a couple of seconds to print a backtrace for one thread.
Couple of seconds?
So, yes. So if you have if you answer request, not process something, but answer request, it may be dangerous. So you may not answer this.
So currently you use the signal-based
yes,
profiler.
in most of our.
What is the? As I understood, is it turned on 24/7 on all your production?
Yes.
And what is the overhead, and how do you?
It is kind of 1%. It is very hard to measure the overhead because it almost you always can't see it because random factors in your system almost
is larger than the measurable effect.
Yes.
Okay, so that's it. That's all my questions. Thank you.
Yeah, we have time for another question.
Thanks for talk, actually, and I would like to ask, is it somehow open source? Can we use it, your solution, or like install on-prem?
Our solution is not open source. There are some open source solution, for example, Profife, but if you have your own infrastructure, it is kind of hard to use an open source solution because you will have some problems with inserting an existing solution to your infrastructure. But if you have something based on Amazon Web Services, I suppose there are some solutions like Profife.
Yeah, actually the Grafana somehow they announced availability of their own solution. It's Flare, it's supporting Go, Rust, Java, Python, so it's basically doing the same like with Flame Graph, etc. So it's kind of there is availability such solution in the market. It is from Grafana. And
this is early development stage Grafana project, and currently they don't have UI, as I know.
They have UI. It's not in. They basically it's announced that it's stable, and they have UI. Basically, it works fine. Yeah.
Okay, yeah. It's fine then.
I also have a question. To use YDB for data storage?
No, we use another infrastructure in Yandex. It is Yandex tables or it. as we call it. But so,
Okay. So, if you have no, we have another question, and we have time for it.
Hi, Igor. As of now, what's your bottleneck of an application?
may you please repeat the question?
Hi, Igor. As of now, what's a bottleneck of your application?
Oh,
As a profiling geek, you must answer. So
it
I'm
is.
interested.
It is.
For a normal workload.
It is a kind of tricky question, and you may think that I'm kidding, but now our problem is with drawing system because we collect too many samples, and our drawing system that draws flame graphs, not collect information, but draws a flame graph, have a lot of problems. They work more than a minute, and it is for some services. I mean, for some very fast services, it works more than a minute, and it is kind of a disaster. So,
Thank you.
After you fix that, you will open source the solution, right?
I suppose I will have the same problem like when you take an open source solution to your proprietary infrastructure, and I will.
If you find protocol, basically you can do open source. Let's say protocol for profiling, there is like you can use Kafka or something else.
Yes, we basically we now use something like Kafka to aggregate streams of stack traces to a single stream, and then we put this data to a table, like a dynamic table.
It's somehow the same like distributed tracing, so very like the jaeger, etc. So they are using the same technology, like they are pushing not the same, but they are pushing the traces to the Kafka, and after they are doing aggregation and doing visualization. So
Yes. We also use Jaeger in our production, but it solves a little different problem. But I understand what you mean. Yes, of course. Thank you.
Okay. So, okay, you have to choose the best question, and we'll give the participant a present. Socks, if I'm not mistaken.
I suppose I have best questions from this person in the first row.
Okay, so our helpers will give you a present a little bit later. And I remind you that after the talk, you can continue all the discussions, and you can continue them in native language. So, so welcome to our zone over there, and thank you for your talk. Thank you very much. You opened the hall, and it's not the easiest task to do. So thank you
for your attention. Thank you for your hosting.